And so, finally, but not least, our next speaker is once again Dr. Marc Dupuis. He contributed to this very, very interesting article, please pay attention to it, called A New Mechanical Model for the Magnetohydrodynamic Instabilities in Aluminium Reduction Cells. The main author is Ibrahim Mohammed, and supported by Professor Douglas Keeley from the University of Rochester. It is a very interesting analytical effort in order to understand the metal pad instability mechanism.
Thank you.
Diagraph slide.
Okay.
Slide.
My bios you gave already.
And you all know Marc.
Yeah.
Please receive Marc.
So sorry, but this paper is only mathematics. So normally I try to avoid, but this one I cannot avoid. I will describe what is a new simplified model to explain the MHD and try to use it as a screen to analyze design space for potential option of changing things and get quick answer. So I will describe what is that model that we call a mobile model, and then I will simply explain how it is developed, and then because I don't have yet exact application. So it started by this Davidson pendulum model that was an innovation like 20 years ago, a bit more, where he was able to explain the principle of instability of a cell by this imaginary device. So this device is a pendulum. So it is this is the point of the rotation, and this is the pendulum itself is a big plate of aluminum, the same size of a cell, and then this thing swing in both directions, so in X and in Y, and then with the geometry of a cryolite is an imaginary cryolite with no friction. And then once you try to assess the stability of this kind of device, did I change the slide? Yes. Okay. So here there's more explanation about where is the pivot and what is the thickness of the different pieces, and what's important here is the center of gravity of this plate, because it's showing up in the equation. And here we have the definition of different parameters, because they were shown in the coming equation. And what's important is the BZ, so it's a uniform magnetic field all over this device, impregnated or uniform everywhere. And so this is the device. You pass current from the anode down. When it's perfectly horizontal, it's uniform current. When you have a perturbation, so when the plate is tilted, then you will get the perturbed current into this plate of metal. And so that's the when it's tilted, it's not stable. You want to go back to the initial position. And this is the equation of the two modes of motion, the X and the Y, and this is the math showing what is those frequency based on the geometry, essentially, and gravity. And here, A is a parameter of stability, you can see, to simplify. Mohammed is calling it, whoops, that's tricky. He's calling it electromagnetic coupling parameter. It's mean the coupling between the magnetic force and the gravity force. And then the critical, what is interesting, A is the parameter of the unit. So you can see an analogy, the parameter of the cell. So it is based on the density of current traveling, J0, the magnetic field, BZ, and then the density of aluminum, and then the geometry, ACD, it's called H0, and H, the height of metal pad. So sorry about those terms, but those physicists, they like to work like that. But on A is the stability parameter, and those are the terms involved, and A critical is the one predicting the threshold of instability. It does not involve even magnetic field if you look at the equation. It is only geometry. And then next I will show that for this pendulum with the dimension or numbers for a typical cell, for us we are using again the 3-met cell, except for BZ, because it's a constant, we have to pick a constant number. So ACD is here, the length, the width of the cell, the metal pad thickness, and then the current density. And then you compute the two numbers, A and A critical, and you get A is much bigger than A critical. That means that this pendulum would be very stable at this, with that geometry of that plate in that system. So it's not very representative as it is now, this pendulum of the reality of a cell. It was very useful because it's explaining why the MHD is working. And now I'm trying to improve on it. So now I'm introducing my new model. And then I have my physicist is doing all the maths for me. That's very convenient. So this, I'm calling it the mobile model. The pivot point is now on the top of the plate, and the center of gravity is a parameter. So the position, because everything is imaginary, so there's no viscosity in the electrolyte. Now the plate of aluminum has a non-uniform density, and so I can adjust the position of the center of gravity of that plate. And I'm doing that for a very specific reason. I want to get closer to the stability of a cell that is I'm trying to represent. So apart from those two changes, it's the same system. But the equations are different because of those changes. So now I have those equations for the gravity mode, and they depend on where the center of gravity is positioned. And n is the position. So n is the value of 0 of n will be the center of gravity is on the pivot point. That means that this thing is completely unstable or will destabilize with a pishnat because there's no gravity effect on it. And then if you approach the center of gravity to the pivot point, it's getting more and more easy to destabilize. And here I need to adjust. I want to adjust this position of the center of gravity so that I'm getting the critical stability at 4.3 centimeter ACD. That is when we have observed at 3-met cell. So it turned out to be 0.16. So I'm getting the center of gravity is getting close to the top. And at that time, the A is crossing the A critical at this ACD. Okay. And then you can run this in MATLAB to confirm that the math is correct. So here I'm running, Ibrahim is running at 1.161, so just above the stability limit. So the system is stable. And then this kind of heartbeat is because of the I don't want to explain because I have 6 minutes, okay. And then so this is critical stability. And then if I reduce ACD, keeping this number for the center of gravity, then I'm getting this very fast acceleration of the perturbation, so I'm unstable. But what is interesting is you're getting this in second almost. So it's very interesting to get kind of interest. But it's still, you see, this result is still far from reality. So now after that, I'm introducing a second innovation to this model. I'm introducing a damping coefficient that is simply put here in that term of the motion of the plate. and then then I had to find a value for this new parameter. So what I did to adjust this parameter is I used the result I obtained with the full 3D open foam model of gravity wave damping, and I was getting a very quick damping, so I used that number or those results to calibrate my friction coefficient. And so I'm asking for 90% damping in one cycle. And of course, here on the left is when you have no damping at all and no magnetic field. Then you start with the perturbation and it will last forever. And now you introduce this 0.35 coefficient and you're getting this damping in 90% damping in one cycle. Now what I do is I put my this friction into the previous solution I was getting with 0.16 for the parameter n for the center of gravity. And now at 4.3 centimeter ACD, I'm getting this damping. Oops. So I'm getting a damping where I don't want one because I want this to be critical stability. So that means I need still to move my center of gravity further up. And that's what we have done next. So we have moved the center of gravity more to now to 0.118. And now with the damping and with the offset, new offset of the center of gravity, I'm getting critical stability at exactly 4.3 centimeter ACD. And now I'm trying like 4.2, I'm getting this slight acceleration so it is unstable, and then I have a growing rate of my perturbation. And now the last thing I'm going to present, I have plenty of time, so I'm talking too fast this time. Here I'm presenting the solution for 4 centimeter ECD that was solved by MHD Valdis for this 3-met cell. And we obtained a growth rate of this number. And now with this pendulum, the mobile model with the friction calibration and with the center of gravity calibration, I'm getting a prediction of this growth rate, so I'm quite close. So that means that even if it's still not perfect and we still have some ideas to further improve it, we have now a simple analytic model that is giving a growth rate in a second that we are planning to use to investigate design space of issue like what we want to analyze the design space of when you modulate your magnetic field to stabilize your cell. So I have 2 parameters. I have my amplitude of this fluctuation, and I have the frequency. And then I published in the last year at TMS, last year at TMS, and it's a result of the PhD of Ibrahim. We know it is stabilizing the cell, this modulation of the magnetic field or the modulation of the amperage, but it's less interesting to do. But with MHD Valdis, we have to wait like 12 hours each point in the design space. So if to analyze the design space of a huge surface, I mean hundreds of potential position, it's not at all practical. But with this kind of a simple model, it will be easy to do. And after that, we could go to an MHD Valdis and analyze the interesting combination of amplitude and frequency. So yes, that's about it. Thank you very much for your attention. Oh, yeah.
Alex.
Thank you, Mark, for this interesting
It's easy to do. Anybody can do it. Now you have everything.
But I didn't, because you show that magnetic field as a constant
Yes.
parameter. So
Because you cannot solve analytically easily. If
yeah,
it's,
so how you investigate real cell? I didn't get how you going to use it for like design.
I am assuming it's representative enough for me to screen option. Like if you compare here, this solution with MHD Valdis, I'm getting at 4 centimeter ACD, I'm getting this growth rate for my my perturbation. So in this very simplified model with yes, the two, yeah, there's another limitation. Yes, the magnetic field is constant, but there's another limitation. I'm only can accommodate 0, 1 and 1, 0 mode, like this and like this. It's not like that in a real cell. So yes, it is not a perfect representation of a real cell, but my claim is that it's enough good tool to investigate this design space.
But in this case, magnetic field, you will use like average as a bias?
Average value, B.
But average is only average of BZ.
Yeah, this is in the equation, and this equation here.
Yeah, so it's only for in case like
I
you represent some bias and investigate ACD, how at which NCD this cell can be stable.
I don't understand your question.
So in using this simplified model, you can estimate only some average BZ, which is, let's say, BZ
yes,
bias, and
yeah,
and impact of, I don't know, metal height and ACD. So this is parameters which you can quickly estimate. Evaluate.
Well, you can investigate any change of those parameters that are in the equation. Yes, ACD, metal pad, average BZ, and yes.
Yeah, thank you.
It's not replacing a true MHD model, for sure. It is a simple investigation tool.
If I may comment on that, Alex? I have the honor of reviewing this one, the best one I reviewed this year. So yes, you are right. The BZ that's represented there is essentially the bias due to the other rows, essentially that. So the only thing that you can possibly test is the sensibility of this arrangement with respect to the bias and the parameters, geometrical parameters that are there. You are right. And the other thing that Marc mentioned is that you can only account for 2 oscillating modes, right? This means that if we are with a beautiful magnetic field leading us to a very high frequency of interface oscillation, so this will not be able to be modeled. But nevertheless, this is a very ingenious article. I strongly recommend to everyone who has an interest in MHD and mathematics. Please read this one. Yes, sir. Last question.
Thanks. It's a really great idea to kind of approximate the MHD behavior. I wanted to ask, for the same parameters you ran the MHD Valdis and this model, how does the frequency of oscillations compare?
They also compare well. I think they are in the paper. I'm not sure, but
I haven't seen it, so I'll see it.
But if they are not annual, I can provide because, and then we're planning to publish more later. The problem is Ibrahim he's done his PhD on this subject, but now as postdoctorate, he's doing something else. So he's doing this kind of work as a hobby. So it's slowing him down a bit.
Okay, thank you.
And with that, we're going to conclude the session. Thank you, Marc. And thank you all for attending. We will go to a little break. Dear Master is going to conclude the session.